This is the first lesson of the organic chemistry unit. So we're going to start by looking at hydrocarbons. What's a hydrocarbon? Well, a hydrocarbon is a compound that contains only hydrogen and carbon atoms. And it belongs to a family of compounds known as organic compounds. Okay, so what are organic compounds? Well, they contain carbon and hydrogen atoms and may combine with oxygen, nitrogen, sulfur, and phosphorus. Your exception is your inorganic polyatomic ions. So we'll write that right there, inorganic polyatomic ions or compounds. So what are inorganic compounds? Well, they're made up of all of the above exceptions plus the substances of the remaining elements of the periodic table. So we have right here a table that compares organic compounds with inorganic compounds. You can pause the video and read it yourself so that you get a sense of what the difference is. Why is carbon so special? Well, carbon has 4 bonding electrons, 4 valence electrons, and this permits carbon to bond with other atoms, forming single, double, and triple bonds. Carbon can also bond with itself, forming chain-like and cyclic structures, and the electronegativity of carbon is similar enough to other common nonmetals, allowing it to form covalent bonds with all of them. Ionic bonds are typically pretty rare in organic chemistry. So today's lesson is going to focus on hydrocarbons, which is this branch of organic chemistry, but there's also hydrocarbon derivatives, and we'll spend some time on these families of organic chemicals. So what is a functional group? Well, a functional group is a particular combination of atoms in a molecule that give the compounds its characteristic physical properties like the solubility, its melting point and boiling point, right, and reactivity. So this defines the organic family. So these are your organic families right here. I'll highlight them for you right here, like your alcohols, your aldehydes, your ketones, your carboxylic acids. Those are called organic families. Okay. Or an organic compound may contain one of these functional groups or multiple of these functional groups. And so we'll see that later on when we get into more advanced videos. Main components of functional groups, multiple bonds between carbons. So if you have a double or a triple bond, you end up with pi electrons, which are above and below the bond axis. And they're more reactive because they are more prone to attacks or more prone to, in a collision, more prone to electron overlap. Okay. Single bonds between carbon and a more electronegative atom. So bonds between these atoms are polar. Since C is partially positive, more electronegative atom will be partially negative. Increasing polarity increases the intramolecular attractions. So your OH groups, your NH groups enable hydrogen bonding, increasing the solubility in polar solvents. And double bonded oxygen and carbon is strongly polarized and creates higher melting points, boiling points, increased solubility in polar solvents. Okay, so that's just like a lot of information about the general ideas of organic chemistry, functional groups. Let's now focus on hydrocarbons. So the functional group of hydrocarbons is the carbon-carbon bond, so the single, double, or triple bond. So we're going to start with aliphatic hydrocarbons. Aliphatic hydrocarbons are classified according to the carbon skeleton into these 3 families. So the 3 families that we have for aliphatic hydrocarbons are alkanes, okay, alkenes, and alkynes. And so alkanes are single bonded carbons, alkenes are double bonded carbons, and alkynes are triple bonded carbons. And the general formula for hydrocarbons, where everything is single bonded, is C sub N H 2 times the number of carbons plus another 2 H's. For double bonded carbon, you have CnH2n. And for a triple bonded carbon, the general formula is Cn2n minus 2. Okay, where N is, again, the number of carbons. So saturation means the max number of hydrogens per carbon. And this only occurs in single bonds. So only alkanes are saturated. Because once you introduce a double bond, then these 2 carbons here do not have the maximum number of hydrogens because they're now bonding twice to carbon. So this becomes unsaturated, and that's also the case with alkynes. Okay, the alkane family. So we're just going to start with just the alkanes. So alkanes are single bonded hydrocarbons, and we'll start with one carbon, CH4. The name we give is methane. The structural formula right there is as follows. So this is its structure. Okay, its condensed structure is just CH4, and there is no line diagram for methane. For ethane, there's two carbons, so put two carbons in the middle. We bond them by a single bond, and then we complete the rest with hydrogens. And that right there is H3C dash CH3. Also, you could write it as H3C, CH3, or you could also write it just as CH3, CH3. Any one of those is acceptable, right? Sometimes it's written as H3C because you can see that there's the three H's right there, and then the C, and the C, and the three H's, so that's typically why that's written. A line diagram looks as follows for ethane. So ethane would simply just be a line like that, where each of these 2 points right here, and typically we don't draw the 2 points, but each of those 2 points right there represent 2 carbons. Draw it again. And then we assume that these carbons right here have the maximum number of hydrogens that they can based on that bonding structure. Okay. So propane, prop is the, not coefficient, rather the prefix that we use for 3 carbons. So we'll do 3 carbons bonded together. And then we fill out the hydrogens right here. Okay, so the structure right there would be H3C, CH2, CH3. Again, you can write it in the other way as well. Line diagram would be, that's 2 carbons right there, and then we go down for the 3rd carbon. Butane is 4 carbons, so we'll go 1, 2, 3, 4, and then we'll fill out all the hydrogens accordingly. Okay, this one would be H3C, CH2, CH2, CH3. You can also continue to abbreviate it by writing H3C bracket CH2 to CH3. And its line diagram would be 1 up, down, and then up again, each of those 4 points representing the carbon. Pentane is 5 carbons, so 1, 2, 3, 4, 5, filling out the hydrogens. Okay, H3C, CH2, 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 CH3. Alternatively, H3C bracket CH2, 3, CH3, and there is pentane for you. Okay, so that just covers the alkanes for the first 5 carbons. We also have what's known as alkyl groups. Alkyl groups are derived from alkanes by the removal of one hydrogen atom, which changes the ending to -il instead of -ane. The alkyl group needs to be joined onto something by a bond, like the example on the right below. Alkyl groups are often referred to as R groups. So a methyl group, so you can see meth meaning 1 carbon. Ethyl group meaning 2 carbons. Propyl group, so on and so forth. Okay, so as you can see right here, this is actually just propane because that is the carbon backbone, also known as the parent chain. And then this right here would be the methyl group. So the methyl group is attached to the propane parent chain. Okay, well, how do we name hydrocarbons? Well, you can pause the video and read the steps here, but we're going to go directly into some examples here. So the example that we're going to start with is 5-butyl-3,3,6-triethyl. In this example, we have 5-butyl-3,3,6-triethyl, 5,7-dimethyldecaine. So we can see right here that this indicates that the parent chain is decane. So I'm going to start us off by drawing out 10 carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And as you can see, I've spaced them out fairly evenly. All right, so that's my parent chain of carbon. Starting from the beginning, 5, so I go to the 5th carbon, 1, 2, 3, 4, 5. I have a butyl group. If you're not sure what butyl is, but is for 4 carbons, so 4 would be butyl. So I have a 4 carbon butyl group, so CH2, 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 CH3. So there we go, so I've got my butyl group. Okay, 3,3,6 triethyl. So triethyl means I have 3 ethyl groups, and they're located on the 3rd, the 3rd, and the 6th carbon. So an ethyl means 2 carbons. The prefix is eth for 2 carbons. Okay, so on my 3rd carbon, I have CH2, CH3. Again, on the 3rd carbon, CH2, CH3. On the 6th carbon, I have CH2, CH3. Okay, 1, 2, 3, 4, 5, 6. Yep, that works out. Okay, and then I have 5,7-dimethyldecaine. Well, the decane was the parent chain right there, so I'm just focusing on the dimethyl. Di meaning 2 methyls, so there's 2 methyl groups, one on the 5th and one on the 7th. So I go 1, 2, 3, 4, 5. I put a methyl group right here, CH3, 6, 7, and a methyl group right here. It doesn't matter if they go up or down because this is all single bonded. The bonds can rotate. And now it's just a matter of adding in the hydrogens. So make sure that your carbon is forming 4 bonds, right? So you add the hydrogens in necessary to make carbon have 4 bonds. All right. And so there's your 5-butyl-3,3,6-triethyl 5,7-dimethyldecaine. We can also do that as a line diagram. So I can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5 on the 5th. 1, 2, 3, 4, 5. I'm going to do butyl. So 1, 2, 3, 4. On the 5th, I also had a methyl, right? So that's my methyl right there. On the 6th, I had an ethyl. Okay, and then over here on the 7th I had another methyl. Okay, and then on the 3rd I had a methyl and an ethyl and an ethyl on the 3rd. Okay, and so there's my line diagram for that. Okay, so drawing hydrocarbons and naming alkenes and alkynes, there's the rules right there. You can pause the video and take a look at that and review it yourself. So this one right here is, as you can see, it's an alkene because it has ENE, so that means it's an alkene, so that means that there's going to be a double bond. So I've got 5 carbons with a double bond. So what I'll do is I'll put 5 carbons out, 1, 2, 3, 4, 5. So I've got the ENE that indicates there's a double bond. The 2 tells me the location of the double bond, so it starts on the 2nd carbon, so 1, 2. So my double bond is over here, okay? And then 4,4-dimethyl, I have 2 methyl groups, both of them on the 4th carbon. So 1, 2, 3, 4. Okay, so I've got my methyl group up here, and I've got my methyl group over here. Okay, and then now it's a matter of just connecting everything with hydrogens and bonds. So H3C, line here, this should be an H, this should be an H, no H's here, and CH3. This can also be done with the line diagram if we do as follows. So up, down, down, double bond is on the second carbon, so I do a double bond on the second carbon, and on the fourth I go up and down for my methyl groups. Okay, so here are some line diagrams. You can practice naming these. Okay, so as always, we start by looking for the longest continuous carbon parent chain. So this is this right here. So that's 5 carbons, all single bonded. So that's pentane. And as you can see, I have a methyl group coming off of that on the third carbon. So I say 3-methyl pentane. Over here, the longest chain is straight across, right here. Okay, and it's a 6-carbon chain, so my backbone is hexane. And then I've got on the second and on the fifth, I've got 2 methyl groups, so I can say 2, 5, and because there's 2 methyl groups, I'll say dimethyl hexane. Okay, in this next one's much trickier because this is the carbon backbone right here. The carbon backbone here has 2 sites of double bonds, so I'm going to say, and then over here I've got a methyl group on the second carbon, so I'm going to say 2-methyl, and then 1 and 3 because that's the location of the double bonds, 1, 3, and then I'm going to say penta because there's 5 carbons, and then I'll say diene, di because there's 2, ene because there's a double bond. Okay, looking at isomers, we have structural or constitutional isomers, which are compounds with the same molecular formula. Okay, but different molecular arrangement. So an example would be butane. Butane is C4H10. You could do it just like this, CH3, CH2, CH2, CH3, that's C4H10. Alternatively, you could draw it out like this. And this would make it a structural isomer. Right, same thing right here, 4 carbons and 10 hydrogens. Names of organic molecules must indicate their structure. So that's why the naming system is so specific and so particular, is because it tells us exactly what the structure is by just reading off the name. Okay, so it doesn't just look at how many carbons and hydrogens there are, it shows us how those carbons and hydrogens are all bonded. So for example here, it says draw the skeleton for all the non-cyclic no-ring isomers of C5H10. Okay, so C5H10, just the carbon cycle, or it's not carbon cycle, rather the carbon skeleton, would just be this 1, 2, 3, 4, 5. That could work out, right? Alternatively, you could do it like this, right? And the last arrangement could be like this. In all of these cases, you will always have C5H12, which makes all 3 of these structural isomers. Finally, you can have geometric isomers. So those are compounds with the same formula, but different geometric orientation. And we'll see in a minute what we mean by this, okay? So this can only occur in alkenes because double bonds cannot rotate, right? Remember that your double bonds do not rotate. We'll talk about triple bonds down here, but your double bonds is where we get these geometric isomers. So as you can see right here, we have cis-2-butene and cis because the chain occurs on the same side, so it rebounds and goes off the same side. Trans-2-butene is where the chain continues on opposite sides of the double bond. So cis means same side, and trans means opposite side. So this means right here, opposite side. Okay, so triple bonds do not rotate either. Do they have cis-trans isomerism? And we'll say no, triple bonds lead to linear geometric orientations, and if they're linear, that means that we don't have the possibility of having, functional groups on either the same side or on opposite sides. Okay, so that's the video. Thanks for watching, and I'll catch you in the next one.